You run explain analyze, see Bitmap Heap Scan in the plan, and your stomach drops. Is it slow? Is the index broken? Should you be worried?
I've definitely felt that panic. What's actually happening under the hood?
Here's the thing. Bitmap Heap Scan is often the planner's smartest choice, not a red flag. Today we're going to decode what recheck conned, rows removed by filter, and heap fetches really mean, so you can judge your own plans in seconds and know exactly what you're looking at. Let's start with the fundamentals. What's a Bitmap Heap Scan, and when does Postgres choose it over other scan methods? A Bitmap Heap Scan is a two-phase operation. First, Postgres scans the index and builds an in-memory bitmap of tuple identifiers, TIDs, that match your where clause. Then it reads the heap pages in physical order, not index order. That's the key difference.
Why go through that extra step? Seems like more work.
Because when you need hundreds or thousands of rows scattered across many pages, reading them in physical disk order is way faster than jumping around the heap following index pointers. You avoid visiting the same page multiple times. That random I/O adds up fast. An index scan follows pointers one tuple at a time, potentially visiting the same heap page over and over. A bitmap heap scan sorts the TIDs, then reads each page exactly once. For selectivity, above about 1%, say, a few thousand rows out of a million, the bitmap approach wins hands down.
So it's not slow, it's just optimized for a different job.
Exactly. The planner picks it when the cost model says random I/O would hurt more than the bitmap overhead. It's making a smart trade-off. Now let's crack open a real plan and decode what each line is telling you. This is where it gets practical. Here's a typical plan. The bitmap index scan ran first, taking 6 milliseconds and touching 65 index buffers. It found 3,147 matching TIDs and passed the bitmap up to the next node.
And the heap blocks line, what's that telling us?
Heap blocks. Exact equals 1,847 means Postgres read that many pages from the heap, with each page being 8 kilobytes, the default size. The bitmap was precise enough that no recheck was needed, as indicated by rows removed by Index Recheck. 0. The buffers line shows all 1,912 pages came from shared buffers, cache hit, total time 42 milliseconds. That's fast for 3,000 rows spread across nearly 2,000 pages. You'd never get that with random I/O. 5 things to check in every bitmap heap scan plan. Heap blocks tells you if the bitmap stayed exact or went lossy. We'll explain lossy in a second. Rows removed by Index Recheck is the smoking gun for lossy bitmaps. Buffers shows cache efficiency. Are you hitting memory or disk? And compare actual time and actual rows to the estimates. A big mismatch means stale stats or a config problem.
Got it. So what's this lossy bitmap thing? That sounds ominous.
This is where people get spooked. Let's demystify recheck conned and what happens when work mem runs out. The bitmap lives in memory, bounded by work mem. If the bitmap grows too large, Postgres switches to lossy mode. Instead of tracking every TID, it tracks whole pages. It's a fallback mechanism.
So it loses precision? That doesn't sound great.
Right. A lossy bitmap says matching rows are somewhere on these pages, not exactly at these TIDs. That means when Postgres reads a lossy page, it has to recheck the index condition against every tuple on that page. That's the recheck con step. Rows that don't match get discarded, and you'll see them counted in rows removed by Index Recheck. That's your signal. Here's a lossy bitmap in action. Heap blocks shows 4,832 exact and 8,471 lossy. That's a lot of lossy pages. Rows removed by Index Recheck is 14,287. Those tuples were on lossy pages but didn't actually match the condition. They got filtered out during the recheck.
Is that bad? Should we be fixing this?
It's not ideal, but it's not a disaster either. The query still ran in under 2 seconds. If you want to eliminate the recheck overhead, you can raise work mem for this session or globally 16 megabytes would likely keep the bitmap exact, but always test. More work mem means more memory per operation, and that can hurt concurrency if you've got a lot of parallel queries. 4 red flags. If rows removed by Index Recheck is more than half your actual row count, you're doing a lot of wasted work. If most of your heap blocks are lossy, the bitmap lost precision early. If the query runs thousands of times a day, even small recheck overhead compounds. And if work mem is set low and you're hitting lossy mode, a modest bump can help.
So it's context dependent. Not every lossy bitmap is a problem.
Always. A few thousand rows removed on a one-off report query? Fine. 50,000 rows removed on a query that runs every second? That's a tuning opportunity. You need to look at the workload, not just the plan. By the way, my DBA's free health check continuously monitors PG stat statements, flags queries that got slower or spilled to disk, and suggests work mem settings for each query based on real plan data. It's continuous analysis that keeps running week after week, not a one-time scan. You get ongoing visibility into what's actually happening. One more thing Bitmap Heap Scan does really well. It lets Postgres efficiently retrieve rows using combined index results. Let's see how that works. Here's an OR condition. Postgres scans IDX orders status, and IDX orders priority in parallel, builds 2 bitmaps, then merges them with BitmapOr. The combined bitmap goes to the Bitmap Heap Scan, which reads each matching page once, clean and efficient.
So it's using both indexes at the same time? That's pretty clever.
Exactly. Without Bitmap Heap Scan, Postgres would have to run 2 separate scans and union the results or fall back to a sequential scan. The bitmap strategy is faster and cleaner. You'll also see bitmap and for-n conditions when combining indexes makes sense. Same idea, different Boolean operation. This is a huge win for schema design. You don't need a composite index for every possible combination of columns in your where clauses. The planner can use multiple single-column indexes efficiently in a query plan when the cost model says it's worth it. That means fewer indexes, less write overhead, and less bloat.
So Bitmap Heap Scan is actually saving us from index sprawl.
Precisely. It's a tool that makes the planner smarter and your schema simpler. You can keep your indexes focused and let the planner do the work. Let's wrap up with a quick decision framework. When you see a Bitmap Heap Scan, here's how to judge it fast. 5 quick checks. First, is the actual time acceptable? If yes, you're done. Second, does the row estimate match reality? If it's off by 10x, run analyze or check for skewed data. Third, are your heap blocks mostly exact or mostly lossy? Fourth, how many rows were removed by recheck? If it's a huge number, you might need more work mem or a better index. Fifth, are you hitting cache or reading from disk? That tells you about your buffer pool.
That's really practical, not just theory.
It's pattern recognition. Once you know what to look for, you can triage a plan in 30 seconds and focus your tuning effort where it actually matters. You're not guessing anymore. Not every Bitmap Heap Scan needs tuning. If the query runs once a day and finishes in 200 milliseconds, leave it alone. Optimize when the query is in your top 10 by total time and PG stat statements, when it's breaching your SLA, or when a plan change caused a regression. Those are the signals that matter.
So trust the planner unless you've got evidence it's wrong.
Exactly. The planner's cost model is pretty good. Your job is to feed it accurate stats, reasonable config, and good indexes, then step in only when the data proves there's a problem. Don't tune for the sake of tuning. Want to catch slow and regressed queries before they hurt? My DB8's free health check connects to your own database in minutes, then continuously collects telemetry and delivers a fresh, comprehensive health report every week, grading you across 16 domains, each finding paired with the exact runnable fix. You'll see which queries got slower, which ones spilled to disk, and suggested work mem settings based on real plan data.
Where do we sign up?
Head to my dba.dev, connect your database, and get your first report in minutes. It keeps growing and keeps coming week after week automatically. See you in the next one.